Glory and honor to our Lord and Savior Jesus Christ. This is going to be a nerd torture session for sure, going through multivariate calculus. The study of mathematics helps us to do great science. Great science helps us to find evidence for a young Earth. And this is just brutal, guys. And it's a cross to bear, so I'm not gonna. There's just no way to put it through. And Lord help us all. If I were teaching this class, I'd open each of my classes and say, guys, I'm praying for you. You need it. But bear your cross. This momentary light affliction is building for us an eternal weight of glory far beyond all comparison. This is just what we have to go through if we're going to engage in professional level creationism. So the relevance of the topic today is that electromagnetic theory is defined by classical electromagnetic theory is defined by Maxwell's equations. So that's kind of the wave nature of light. Not really exactly. We could say quantum mechanics is the kind of the particle nature, but that's not exact. The most full description we have so far is quantum electrodynamics. It would encompass, I guess, the wave and particle nature of light. But classical electromagnetism is definitely the studying the wave nature. It models light as a wave, not as particles. And if we're young earthers, there have been a variety of suggestions to solve the distant starlight problem. Some of them are appeals to modifying Maxwell's equations. One of those proposed is the Hertzian version, which is very close to Maxwell. Hertz vindicated a lot of Maxwell when he made Maxwell's equations when he made radio waves. So there's a lot going on in this. So we're going to go the classical route. So notwithstanding that I'm saying it may not be the most complete theory, for 99.9% of everyday electrical engineering and everyday applications for building generators, motors, radio transmission, classical electromagnetism is good enough. It's going to be good enough, God willing, to analyze the problem of geomagnetism. You look up Wikipedia, we see that geomagnetism, the geomagnetic field may decay in 1600 years, which would suggest the Earth is young, despite claims that over millions of years it was stable, but I'm trying to point out that's based on circular reasoning. We actually have good measurements from, like, say, the last 150 to 200 years on the strength of the geomagnetic field. We don't have direct measurements for like 7,000, much less millions of years ago. So when they claim that they've measured it millions of years ago, that is circular reasoning. It's based on assumption. It was not a direct measurement, and historically, handed down. For all we know, it's storytelling. I mean, I'm not trying to say it's nefarious. It was a sincere try, but it's built on assumptions, and if they're false, it will end up being storytelling. So to do electromagnetism, it requires multivariate calculus, and it was 30 years ago, Scott, 30 years ago since I did electromagnetism. And I've done multivariate calculus, but it's still like, some of those operators like curl, I've done a little bit of the Laplacians, but it's been a while, guys. And Dr. Russell Humphreys is coming on this channel to talk about electromagnetism, and there'll be others. I owe it to these individuals to at least show some effort, and we'll just see where this goes. So to that end, let me just start from the start, and there's just like no beautiful way to start at this, okay? It's all going to be ugly. So let's just start with multivariate calculus. Multivariate calculus. Multivariable calculus is right. Let's do it, baby. Lord, help us to bear our cross each day. This is a cross to bear, no kidding. Multivariable calculus, also known as multivariate calculus, is the extension of calculus in one variable to calculus with functions of several variables. The differentiation and integration of functions involving several variables rather than just one. Multivariable calculus may be thought as an elementary part of advanced calculus. For advanced calculus, see calculus on Euclidean space. We'll just skip that for now. And I'm going to skip all this. There's a lot of stuff here. This is just, okay. So when you hear the word partial differentiation, let's make this a little bigger. When we hear the word partial differentiation, that pertains to differentiation in multivariable, in the multivariable arena. So the partial derivative generalizes the notion of the derivative to higher dimensions. A partial derivative of a multivariable function is a derivative with respect to one variable with all other variables held constant. Okay. Partial derivatives may be combined in interesting ways to create more complicated expressions of the derivative. In vector calculus, the del operator is used to define the concepts of gradient, divergence, and curl in terms of partial derivatives. A matrix of partial derivatives, the Jacobian matrix, may be used to represent the derivative of a function between two spaces of arbitrary dimension. Whoa, okay. Jacobians are kind of like nasty. I used them in one class I did on robotics and also probability theory. Its application in robotics is kind of cool. You need Jacobian matrices, so when the robot's arm's moving around and it's computing, how to position the arm, it has to go through a Jacobian matrix. But still, it's not pleasant stuff, guys. A matrix of partial derivatives, the Jacobian matrix, may be used to represent the derivative of a function between two spaces of arbitrary dimension. The derivative can thus be understood as a linear transformation which directly varies from point to point in the domain of the function. Differential equations containing partial derivatives are called partial differential equations, or PDEs. These equations are generally more difficult to solve than ordinary differential equations, which contain derivatives with respect to only one variable. Holy cow! I kept hearing those terms, and now it's kind of like I didn't see the forest through the trees. Now I know the distinction. PDEs, partial differential equations. Ordinary differential equations are just one variable, at least according to this wiki article. Everyone will have maybe slight nuances in their definition. It's good enough for our purposes. So there is a thing called multiple integration. Not doing that really. Okay, this is interesting. In a lot of electromagnetic theory, you're just doing partial derivatives. I haven't seen a lot of integration, at least at the level that I'm doing stuff. Thank God. Derivatives are always a little easier than integrations, in my opinion. Okay, so there is the fundamental theorem of calculus in multiple dimensions. The gradient theorem, Stokes theorem, divergence theorem, Green's theorem. Okay, I'm familiar with the divergence theorem, Stokes theorem, gradient theorem, Green's theorem, nope. Maybe I've seen it before, but oh well. So, kind of the basics that I need to get reacquainted with is scalar fields. It's a function from Rn to R, and I'll explain that. And vector fields are Rm to Rn. Really, it's from R3 to R3, usually. Usually for electromagnetism. So yes, there is Rm to Rn, where m and n are integers greater than 1. But for electromagnetism, it's R3 to R3, and I'll explain what that is. I didn't know they have these other things like curves, the R to Rn. That's interesting. And then R2 to Rn, surfaces. I'm not going to be worrying about those. So I'm just going to stop here. I know I'm blasting through this. So you'll hear the word tuple and the word vector. And just how this fits in, I think you might figure it out. So in mathematics, a tuple is a finite ordered list of elements. An n-tuple is a sequence or ordered list of n elements where n is a non-negative integer. Non-negative integer. There's only one zero tuple referred to as the empty tuple. An n-tuple is defined inductively using the construction of an ordered pair. Okay, I did that construction once in a math class. It was interesting. It was just, I was like, I know you're trying to be rigorous, but this is like rigor mortis. You're being so exact. Okay, so they tried to justify the construction of n-tuples with this. So in electromagnetism, you have three coordinates a lot, x, y, and z, x, y, and z. And so when you have a three tuple x, y, and z, the x coordinate, comma, y coordinate, z coordinate, x coordinate, comma, y coordinate, comma, and the z, that's a three tuple to describe like a vector or a point in space, either a point in space or a vector. And sometimes a point in space in R3, three-dimensional space. Okay, so when they were saying R3, that means a three-dimensional space that is the points are defined on the real number. You can build all sorts of spaces where you're not using the real number system. You can do it with what they call fields. They're axioms of a field. Just complex stuff, guys. We don't need. The mathematicians love getting into that stuff. We're physicists, right? So we're not going to get down into those weeds. But we're physicists and engineers. Engineers, by the way, I consider applied physicists. So mathematicians usually write tuples by listing elements within parentheses and separated by commas. For example, 27417 denotes a five tuple. Okay, we don't have to go really deep into this. So a triple. So they don't even call it a tuple, or three tuple. They just call it a triple or triplet or triad ordered triple. A threesome, a treble. Okay, so in electromagnetic theory, we're going to do a lot of that. And let me see what they have to say. They have some real formalists here. I mean, there are applications for this. So, I mean, don't get me, I'm not trying to minimize the hard and brutal work that these guys have done. I'm just saying in terms of today's applications, in terms of modern day engineering, the triplet, the ordered pair, vectors in three spaces is very, very, very common. I think in some classical mechanics, you'll have three positions and then three velocities or three momentum. In classical mechanics, you'd have these six tuples, six-dimensional spaces. What do they call that? A sextuple, a sextuple, hextuple or hexad. A sextuple, hextuple. I like that. Hextuple or hexad, a hexad. Tuple. Okay. The term originated as an abstraction of the sequence. The prefixes are Latin. I don't know where tuple comes from. Okay, so it does say here, I was looking at the word vector. The term tuple can often occur when discussing other mathematical objects such as vectors. Okay, so now I'm going to go to the wiki entry on vectors. So let's go to vectors. I mean, there's probably a distinction between a vector and a three tuple, but the notation looks so similar, I'm just not going to care. A vector. In mathematics and physics, a vector is a term that refers colloquially to some quantities that cannot be expressed by a single number, a scalar. So something that can be expressed as a single number is a scalar, or to elements of some vector spaces. Historically, okay, vector spaces that's another headache, okay? I'm not going to go there right now. Historically, vectors were introduced in geometry and physics, typically in mechanics, for quantities that have both a magnitude and direction, such as displacement, forces, and velocity. Such quantities are represented by geometric vectors in the same way as distances, masses, and time are represented by real numbers. The term vector is also used in some contexts for tuples, which are finite sequences of numbers of a fixed length. The term vector is also used in some contexts for tuples. Both geometric vectors and tuples can be added and scaled, and these vector operations led to the concept of a vector space, which is a set equipped with a vector addition and scalar multiplication that satisfies some axioms generalizing the main properties of operations on the above sorts of vectors. A vector space formed by geometric vectors is called Euclidean vector space, and vector space formed by tuples and is called a coordinate vector space. I'm sorry I have to vent a little bit. You know, some people have said I'm a fraud, and it really bothered me. Losers like Nathan Orman and Mike Brusanak, you guys are scum. Sorry. Just had to point that out. You know, it's just been 30 years since I've done some of this, really. And you're going to just start advertising that I'm a fraud. And dude, I just think you guys are losers, especially pudding brains. Just had to say that because it really gets under my skin that you guys say stuff like that. And so just take that, you losers. So anyway, we'll go on. So now we've done the vectors. The definition of a vector space is pretty nasty. So a vector space, oh well. All right, we'll just do, I mean, it's a tough definition, you know, in my linear algebra book. So we're taking the concepts in vector spaces and we're going to start using vector operations that are used a lot in electromagnetism. And it, oh, and I need to cover something that talks about vector calculus. So I said vector calculus is one form of multivariable calculus. So you saw there's calculus involved in a scalar field, and then there's calculus involved in the vector field. Electromagnetism goes into both areas. So vector calculus is a subset of multivariable calculus. Multivariable calculus is not solely vector calculus. If you build a Venn diagram, you can do that. So let's look at the oops, that's not what I needed. Let me just delete that. Let me clean up a little bit. Okay. So lecture 5, vector operators, grad, div, and curl. And we use a lot of this. In the first lecture of the second part of this course, we move, this is a great, this is, by the way, in the video description. In the first, and this is such a good description. I liked it. In the first lecture of the second part of this course, we moved to consider properties of fields. We introduced 3 field operators which reveal interesting collective field properties. V's, whatever V's means. The gradient of a scalar field, the divergence of a vector field, and the curl of a vector field. There are 2 points to get over about each. The mechanics of taking the grad, div, or curl, for which you will need to brush up your multivariate calculus. The underlying physical meaning, that is, why they are worth bothering about. In lecture 6, we'll look at combining these vector operators. Okay, let me go grab my electromagnetic theory book and I'll show you something. I'll be right back. I'll grab it from my library here. So let me see if I could show it here. So you hear the terms divergence, gradient, and curl, and Laplacian. And the book is Engineering Electromagnetics by William Haidt, 5th edition. I mean, this was, you could see this book is well worn because it's just been bumped around in storage and so forth. I occasionally reference it. You know, now we're going to go and work through these operations. So when we're trying to deal with geomagnetism, which Russell Humphreys will be helping me do a series on that, you have to get through all the electromagnetism, and it's not pleasant. So we have gradients, and so the result of a gradient, let me see what the result of a gradient is. I wish they had a little bit better worked out example. Does it return a, I don't like this too much. Oh, here it is. The gradient of so x looks like it is a scalar, x squared, and the gradient of x squared equals a vector. Okay, so this is helpful. We start off with a scalar, we end up with a vector. Divergence, we start off with a vector, and we end up with a scalar, a number, physical, a number. Can be expressed as a number. And going back to the thing of tuples, I think a one-tuple, I wonder if we could say a scalar is a one-tuple. I'm just curious. Tuples. I'm going to just look at it again. Monopole, a singleton, a monad. I'm just going to singleton. See if a singleton can be said to be a scalar. So someone has been asking this if scalars are singletons. I guess I'll let the philosophers of math resolve that. So we have, just think of it as getting a number. But when you have a vector, you'll have three numbers, an ordered triplet of three numbers. And so that's the divergence. And then a Laplacian, let's see what you get. One gets a scalar. So I think you start off, recall that the grad U of any scalar field U is a vector field. Recall also that we can compute the divergence of a vector field. So we can certainly compute the divergence and the grad U even if we don't know yet what it means. So we start off with if U is a vector field, we start off with a vector field. We get the grad of a U. No, we start off with a scalar field U. I'm sorry. Start off with a scalar field. We get that generates a vector field. So U is a scalar field. Grad U is a vector field. Div grad U is a scalar field. So that's why you get that. And I'm sorry, I need to, that's a little painful here. This actually deals with special relativity. I actually was doing a Laplacian operation. Let's see. So I'm in the middle of writing just an educational paper. I'm not going to try to, let me digress a little bit because I need to just rest my brain a little bit. Here's a magnificent picture of the founders of modern physics. There's Einstein, and to his right is Lorentz. These two are just big deals in relativity. Relativity, special relativity is expressed with the Lorentz transform. There's Madame Curie. There's Max Planck there somewhere. Oh my goodness, there's so many of the great ones. Max Born. Schrodinger is there. I think that's probably Schrodinger. Who else? Heisenberg is somewhere there. And they're just some absolute. These were all top notch. Incredible. We could get all of them in one meeting. So the Lorentz transform, I was working on that. If you take the equations of electromagnetism, one can then show special relativity. And I was using, there it is, that's the Laplacian. And so the scalar field is the electric field, and I take a Laplacian of the electric field. And I could show that time changes the ticking of your clock changes depending on your velocity. That's what that was doing. So some say time flows differently. That's what you'll get in the textbook. I'm going to argue the clock just ticks differently because of that relationship. So when you hear the Laplacian, this is me doing taking the Laplacian is just miserable, guys. Okay, this is the Laplacian. Okay, I mean the DLM version is related to the Laplacian. So let me see if I even have it here. This is just brutal. I mean, this is not, math is not easy reading, guys. it may be on just one page, but I have to crawl through it to figure out what it says. It's like sipping, sipping that delicate wine. You just take it in small pieces. So you can see the Laplacian operator here on the electric field. And then as you work through it, you're going to derive the Lorentz transformation of special relativity, which was the big breakthrough where they started to say time is relative. I would say really, I mean, personally, and this is subject to verification, I really just think there's an absolute clock. And the reason I'm arguing for an absolute clock is quantum mechanics prefers it. And Sabine Hassenfelder, or I can't pronounce her name, she said general relativity can't quite be right because quantum mechanics wants an absolute clock, wants an absolute time. There has to be absolute time for quantum mechanics to work. And so therefore, all this thing about time flows differently, it's better to say clocks flow differently because there's an absolute clock. It's as simple as that. And you can actually argue, I'm going to argue using these Laplacians and whatever, that you can just as well argue that the clocks tick differently. I'm going to make an argument based on acceleration as we go to different frames, just based on electromagnetic theory. So I digress a little bit. I just had the point where, this stuff will start to touch on really cool stuff. So now, but unfortunately, we have to crawl before we can walk, and we have to walk before we could run. And the minister said, well, before we can crawl, we need some money. Need some donations. Sorry, that was a joke from Flip Wilson a long time ago. Anyway, so now let's go through the mechanics of this. So the grad operator, the gradient of a scalar field. Recall the discussion of temperature distribution throughout a room in the overview, where we wondered how a scalar would vary as we moved off in an arbitrary direction. Here we find out how. So if U of R it really should be identically U x y z is a scalar field. All right, I'm just going to uncoil this. This is let me go back to that multivariate calculus here. So in kind of basic calculus, single variable calculus, we normally, actually, let's see, x and f of x. We call it f of x So we have a lot of graphs. Let me see if I could show it. I wish they had better. Just a simple thing with a graph labeled. And I'm doing this just to help myself also. So the axes, let me see if I could find a better one. A little obnoxious here. Oh, here we go. Here's a better one. Hang on, guys. So this is pre-calculus here. Delete that. Delete that. Delete that. I'm going to pull that out. So we have x, and it maps to f of x. Now, in two-dimensional space, you can actually visualize. You can visualize this. You can actually put the two on the same sheet of paper, where you get x and then y. You know, the x-axis here, f of x, and you can put it on a piece of paper. For a gradient field, it is not so. For a vector field mapping to a gradient field, or no, for a scalar field, I'm sorry. Boy, I'm really messing up, guys, sorry. For a scalar field that is 3 dimensions mapping into a vector field that is 3 dimensions, this is tough. Because how do you do f of x, y, z into a vector x, y, z? This is not nice. I mean, you would have to be thinking in 6 dimensions. Okay, so when you're going from f of x versus x, f of x is a function of x. You can visualize it in 2 dimensions because we can, we live in 3-dimensional space. But when you go from 3 dimensions to another 3 dimensions, your brain can't quite handle that. You can't visualize it. There's no nice way of visualizing it. So imagine like my house here, I could take a thermometer and there'll be slightly different temperatures, at a given slice of time, at a given instance of time. There's slight variations in temperature, certainly like near the light bulbs. And you could plot the temperature at each of those X, Y, Z points. And then that would map to, at each X, Y, Z point, the temperature is either going to be going down or up according to, what direction you're headed. So the gradient will say, it's kind of like the slope, but again, you're dealing with 6 dimensions here. It's just really hard to visualize. So just imagine, I mean, maybe one way to see it is you have all these points of temperature, and at each point of temperature, you'll have also a vector of a certain length. So that vector, that length, you'll have kind of like, it's just, I mean, it's a visualization, but it can be a little confusing. So when you look at the vector space, so when you take this gradient, the gradient of a scalar field, so the temperature of all the positions here, the gradient of that will map to a vector space whose origin is at 0, and the vectors will all point from that 0 origin. But you can kind of cheat and take that 0 origin and just kind of put it at all, at all the points in my room. So you'll have this, for lack of it, you could just, at every point you'll have this, you'll have another vector. If you put you put a vector at each point, you'll start to see it. So maybe to illustrate kind of what it might look like in 2 dimensions, let me dig that up for you guys. It's a little miserable. I'll do it in 2 dimensions vector. You see, and I think I had a picture of it. Oh, here. Here's a vector. This is where you could take a gradient. All right. All right, let me try to put this up for you guys. See it there? So yeah, so just imagine you have XYZ, whether you like the way they did the coordinates or not. You can take an XYZ point, and at each point, you do the gradient, and then you can calculate a vector, and from that point you just put the vector somewhere on that point. It'll have the magnitude and the direction. Again, it's not, there's a little cheating here, okay, just to help you try to visualize a little bit. But technically speaking, each point will map to a separate codomain vector in a vector space. It's just, okay, I mean, the numbers work out, but you know, when we try to do visualizations like this, it's you know, you kind of have to cheat a little bit so that you could see what kind of the qualitatively what's trying to be communicated by doing the gradient operation. So if I have a room with different temperatures, I can run the gradient, and then I can build all these little vectors that are showing how the temperature is changing, like say increasing. So this is the increasing direction here in the magnitude of it. It is, I'd say, I hope I'm right. I think it's kind of like a first derivative in single variable calculus. Single variable calculus is kind of like a first derivative, but now you have to add not just the first derivative in terms of magnitude, but you also have to have a very specific direction in three-dimensional space. All right, so we've just gotten kind of through gradients, and this is just something to think about. And we can go through the math at some point, but I think it's helpful to just go through qualitatively this. Going back here, all right. So we can calculate the gradient of the scalar field. Why don't we go through this? The gradient of the scalar field is the partial derivative of u with respect to x. And I'm sorry, guys, this is where you actually have to know how to do partial derivatives. And it's been a while since I've done them. I have to keep practicing. So you have a multivariate function, you know, that's in terms of x, y, z. And then you have to take a derivative with respect to x. And then you multiply that derivative by the unit vector I. And then j and k. Okay, this is where it gets confusing. So to make this vector field, we have these unit vectors. Okay, so remember, you have the domain, which is x, y, z, and then you have the codomain, which is unfortunately also sort of x, y, z. It's better to, I don't know what you're going to call it. F of, what would you call that? The codomain. You would unfortunately also use XYZ. You have XYZ for your scalar field, and in your codomain you also use XYZ to describe it. I don't know, would they, because it's let me see, I'm trying to think. It's not quite, you know, IJK are unit vectors in that. Okay, so XYZ, let's call that the domain. XYZ, you know, with a subscript domain, X domain, Y domain, Z domain, just to make it clear. In the codomain, just say X codomain, Y codomain, Z codomain, or you could call it range. Sometimes they use the word range. And there's a little bit of confusion because at least when you're doing single variable calculus, f of x is usually told to be on the y coordinate. And it just gets really confusing, guys. You could say the, you know, you might say x domain and then x codomain or something like that. There's just some unfortunate historical usages that you know, the notation ends up being a little bit confusing, and intuitively you start to figure it out and you just don't care at some point. You're able to get through it. So with the I, J, and K, just think of it I, J, K in this codomain, this vector space. I has it's a unit vector that is of length 1 in the x direction and 0 in all the others. And then J is unit vector with length 1 with the point, the vector at 1 in the y direction and 0 elsewhere. And then the k vector is 0 in the x, 0 in the y, and 1 in the z direction. So let me see if I could find unit vectors. And I wish someone had really just, you know, it's easy to get really lost in this. Unit vector. Let's just try a unit vector XYZ. See if I can get a diagram of that. So let's bring this up. That's what I was saying. I goes along the x direction, J is the y, and K. So those are the unit vectors. And this is where it would be good to have someone in the class to you know, we're just gonna, you know, the problem is in school, you're limited to your time and you can't really take the questions, but this, you know, everyone has kind of their pace of understanding because they come at different points, and that kind of makes it a little hard. So I hope I didn't blast away what I was trying to show. Okay, then let's just separate this out. All right, so I, J, K. So you have I, J, K. So now let's go back to doing this calculation. See, the nice thing, when I was going through school, I didn't have to be, I had to cheat, so to speak, not in the ethical cheating. I mean, cheating in the sense that I really didn't understand kind of like the visualization of what the equations meant. So, I mean, ethically, I did things straight up, but I didn't. What was frustrating is I was good enough at the math that I could do the math without understanding what it was describing. So like when I was showing you those vector fields that came from the gradient, I didn't necessarily visualize what the math was describing. I could just kind of do the differentiations and just plug and chug. But what it meant, I'm just like, I don't know. So now we're gonna go through this mechanically now that we know what we're trying to describe. So we take the derivative of u of r. Okay, so sometimes in electrical engineering notation, we wouldn't just use u, we'd actually say u of r or u of xyz. And I might do that at some point, but you know, let's just move forward. And this is giving me ideas of how to present this. We have like, the scalar field space and then the vector codomain space and show how it maps. And if I could do like say a 3D visualization, you can actually see it and the equations will start to make a little more sense. But if we don't have an animation of this, barring that, we would try to use pictures like this that are, can be misleading, and it can help to a point, but then it will lead to some misunderstanding at another point. So, it comes at a price for doing business that way. But yeah, so going, this thing here, it'll come at a price because it's not really exact. It can be misleading. But it's, it still helps. I'm not minimizing that. In the absence of animation, that's about as good as you can do it. So anyway, so let's continue here. It is usual to define the vector operator, which is called del or nabla. I hardly ever know anyone that uses the word nabla. The little nabla as I times the derivative of x plus j times the partial derivative y, k partial derivative z. Del operator. So the grad u is the del times, is this operator on that. Note immediately that del u is a vector field. Without thinking too carefully about it, we can see that the gradient of a scalar field tends to point in the direction of the greatest change of the field. Later we'll be more precise. So what that sentence means is kind of like what this picture is showing. All right. Again, there's some subtleties here. And if it confuses you, that's okay. It's easier if I could show an animation and you'll see it. So now let's work out an example of gradient evolution. U equals x squared. U equals x squared. So again, U is a function of x, y, and z. Maybe to make this easier, you'd say U equals x squared plus 0y plus 0z, something like that. Because then you could see that you are trying to make it a function of x, y, z. But it will reduce to U equals x squared. So now let's do a partial derivative of this. The partial of x, the partial derivative of x squared with respect to x is 2x, and then you multiply it by I. Partial derivative of x squared with respect to y is 0, so that zeroes out. Partial derivative of x squared with respect to z is 0, so that zeroes out. And yeah, so we take, I could expand this and you'll see it. And you get 2xi. I was a little sloppy in the way I said that. And then we can also do r. U equals r squared, where r squared equals x squared plus y squared plus z squared. And that's going to be a lot nastier. No, it's not so bad, actually. So you get 2r. This is unfortunate that they said 2r. I don't know where they defined r. Oh, here it is. R equals xyz in 3 dimensions. R equals xyz in 3 dimensions. So we could just say 2r. I think you can only do that if you have all of the coefficients, 2x, 2y, 2z, x, y, z. Yeah, 2r equals, r equals, I think that is just slightly sloppy. R is equal to x times, unit vector I, y times j, and z times k. Then, yeah, that is a little, this is a little just a tad sloppy here. That's just a tad sloppy. That's just my objection there. See, because again, the XYZ and the XYZ here is in the codomain. This is the XYZ in the domain. That's why this is a little confusing. Is the XYZ in the domain or the codomain, or what we sometimes call the codomain is also in the olden days when I was going through school, codomain was called range. So we had range and we had domain and range. Okay. So here's another example. All right. Example 3. I don't know what NB means. NB not U of R. U equals U of R. It is NB. I don't know what NB is. See, I think like this R, I don't know. You can work through the math. I can clean this up a little bit if I wanted to redo this. So the significance of gradient, I'm just going to skip that. We at least know how to do the math. And now we do the divergence. And we'll revisit this. The divergence computes a scalar quantity from a vector field by differentiation. The div of A equals partial of A1 times partial of A2, partial of A3. See, this is better notation. If A, XYZ is a vector function, the position is 3 dimensions, that is A equals A, okay. 1 is a vector. So when you have the bolded, it is a vector, where you also have unit vectors, you're multiplying it by unit vectors. Okay, that helps you. So I think now when it says NB here, not bolded, NB is not bolded, not UR. He could have used better terms. I'm just going to assume NB means not bolded. So here we start off with a vector. So the partial of A1 with respect to X. So A1, you actually just use the coefficient. You drop, you're essentially not going to include the unit vectors there. And you do partial derivatives. And then you end up with a scalar. I'm going to, because it's getting late, I'm going to skip all the derivation and we'll just revisit divergence. But where was I headed with this? Divergence theorem. This is one of Maxwell's equations, about the only one I still know by heart. Divergence theorem, Maxwell's equations. of electromagnetic theory. So the divergence theorem, I think, is this one. That's the divergence theorem. No, that's, where is it? Yeah, charge enclosed. This is the divergence theorem. Let's see. I'll go back, Maxwell's equations. So if you're building lasers, you need some of this, and then some quantum mechanics, and then you'll have all the headaches you need. This aspect of creationism is not easy, guys. Goodness. What's happening? Open, image in new tab, Gauss's law. Okay, Gauss's law. Let's look at Gauss's law. Gauss's law. Yep, see, there it is. So Gauss's law is one of Maxwell's equations, and it says relevant, a mathematical theorem relevant to all these laws. See the divergence theorem. See the divergence theorem. So this is it right here. We can use the divergence theorem. That's the integral form. That's the differential form, the Gauss's law, and you have the divergence operator right there on the electric field. And going back to our computation here, this is how you will do. See, you have a del dot A. Instead, you have a del dot E. You're just substituting, the symbols. And so there's the first equation of Maxwell's equation using vector calculus. And then we're going to go through all these, and then you basically have the elements of electromagnetic theory. This is hard enough. You could see we got through here. And do we have any gradients here? I don't see it. So we can use the divergence theorem here. And let's see, Gauss's law for magnetism, that's another divergence theorem. Let me just make sure I got that right. And see if it uses the divergence theorem. Okay, so we got two of Maxwell's equations. We had the method, so we'll cover that. And then we have the curls is the next operator. So you can do a lot of electromagnetism if you can do the curl operator, if you can do the divergence operator, or the divergence operation. I'll have to look back, or the curl. And then you have at least the skill set to state Maxwell's equations. Not that this is necessarily nice to state. I mean, I think even if you didn't understand what these symbols mean, it's certainly within the realm of capability to, if you spent an hour, like you put that little upside down triangle and put a dot and an E, and then you say rho over epsilon 0. And this one's really, that's probably the easiest of Maxwell's equations, del dot B. Even if you don't know what B or E is, you can still memorize it. This one gets a little gnarly here, and then this one's definitely, this one takes the cake. That unifies the electric field, currents, and the magnetic field, and you create you create an electromagnetic wave. It unifies electricity, magnetism, and optics, which is just like way cool, way cooler than evolutionary theory, you know. So that's real science. So what Russell Humphreys is probably going to be dealing with is a lot of this right here. The the Maxwell-Faraday equation, and then Gauss's law for magnetism. We'll have to ask him which one of these. Now, I had shown a little earlier, let me see if I have it here. Where I was dealing with relativity, that's kind of definitely at the high end, and you're using Laplacians to describe stuff, and it's going to get you some really curious results in relativity. And I was trying to solve those equations, you know, solving for some of the variables, and I was getting all these transcendental results. It was incredible. But you know, this is taking from basic calculus, and you're just kind of building up in multiple dimensions, and you just have to have the accounting, what you're dealing with. You know, when you're dealing a scalar field as a domain, and your codomain is a vector space, and then you switch it for divergence. You start off with a vector space as your domain, and your codomain is a scalar field, I think. No, it might even just be a single number. I have to think about that. I'll just have to think about it. Might be a single number. The nice thing is the second of Maxwell's equations, the scalar field is all zero, which is really nice. Which you can see here. So we'll work through some of these examples. If I said something wrong, please correct it in the comment section. And yeah, so that's what we're gonna do. And we'll just say that we've already gone for an hour, 10 minutes. So in a typical college class, this would be like having a Tuesday and Thursday lecture. So this is one, you know, if you have 2 meetings a week, you'd have an hour, 15-minute class. So we covered an awful lot of ground. And if I were teaching this, I'd want to be more interactive and just say, you know, try to work with the students, you know, kind of tutor them. Because in the classroom, everyone is learning at a different speed because their starting point is not the same starting line. And then obviously some of them have different levels of ability. The idea is to get them all across the finish line eventually, but it can be frustrating because some are just so far behind. And that's why I enjoy tutoring more than classroom lectures. So for today, I was just really teaching myself. So let us honor and glory to our Lord and Savior Jesus Christ for helping us bear this cross to get through it. I know, guys, it's sometimes tough to be doing all this when our world is falling apart, and you know, we long for happily ever after, and the threat of nuclear war is somewhere on the horizon. But you know, Jesus said, "Occupy till He returns," and we're doing just that. So thank you all for joining this stream. Take care. The Lord richly bless you, and I'll just finish. I'll finish this with maybe just kind of one of my more favorite endings. Picture of me and my dad. God bless you. Have a good day.